talked about the fact that we need to look at the distribution of the molecules. Okay? So the distribution amongst the various energy modes is described by the Boltzmann equation. Okay? And so this is our Boltzmann equation. So the Boltzmann equation of the Boltzmann factor, the Boltzmann equation, the Boltzmann fraction, they're all commonly used. This describes the fraction of the number density in the ith energy state compared to the total number density. Okay? And so again, let's just make sure that we understand what we have here. We have n sub I, that's the number density in the ith state, the total number density. We have the degeneracy of state I, okay? And then we have the energy, we have the ith energy state, the Boltzmann constant, and temperature. And so when we take any transition I, we sum them up. This is the total energy, okay? And then we just look at the fraction that's in the ith energy state. Now this can be applied to all different, this can be applied to the rotational states, the vibrational states, the electronic states. Okay? And so the denominator here is what's termed the partition function, and it's denoted Q, which is Q again. We have a lot of Q's. We'll actually have another Q later. Q is used a lot. So this is not quenching. This is just the terminology used to use the partition function. But I use Q because that's what's used within the literature. Now, based on the assumption that the translational, electronic, vibrational, and rotational modes are all equilibrated, our total partition function can be written as the product of the electronic, vibrational, and rotational partition function. And we leave out translational energy because it's not quantized, unless you consider a really small box. That's kind of like a theoretical physicist type issue. If you get a really tiny box, you can say translational energy is quantized. So what we can do is say that the distribution of the population of all rotational levels within a given vibrational state, we can consider those individually. So again, we'll look at all the rotational levels within a given vibrational state. Then we can look at all the different vibrational states within an electronic state. Or what we can do is just say that our fraction, okay, in the ith state is just equal to the product of the fraction that's in any given electronic state, any given vibrational state, and any given rotational state. And as you can imagine, all you're going to do is you have, if you're talking about the ground electronic state, obviously this is going to be a large fraction. We'll show that it's pretty close to 1. This will get smaller, and this will get smaller. And you can think about this just based on if we're dealing with a single electronic state, then we have a certain number of vibrational states. Within each vibrational state, we have many rotational states. Okay? So the fraction of population in any given combination of a single rotational state within a single vibrational state within a single electronic state has to be much, much less than 1. Okay? These are then now the definitions of our Boltzmann fractions for the electronic state, the vibrational state, and the rotational state. Okay? These describe their various energies. Okay, this is the energy in the mth electronic state. This is the energy in the vth vibrational state and in the jth rotational state. Okay? In each one of these, we have to get the partition functions for the electronic, the vibrational, and the rotational state. All right, so let's start with the electronic state. So this is the electronic partition function. M is just the principal quantum number, and Gm is the degeneracy of that electronic state M. Okay? And remember, our degeneracy was if there were multiple possible electronic configurations that have the same energy. Okay? So if there's only one way by which the electrons can occupy the orbital, there's no degeneracy. But if there's multiple states that have the same energy, we said that was a degenerate state. Okay? And then that has to be accounted for. But we'll see that it kind of cancels out in a second, so it's actually, we don't have to account for it. So let's say we want to find the change in energy or the delta M for the mth electronic state. In atoms, E1 in the ground state is set equal by convention, is just set 0, so everything's relative to the ground state. In diatomics, this is not true, because what happens is if we looked at that vibrational level, go back and look at your notes at some point, you'll see that the 0, there was a portion of the potential energy curve that actually went below 0, and this is to allow for dissociation. Okay? And so this is kind of like a after-the-fact fix, if you will. So if E1 is equal to 0, then the partition function of the electronic state is just the degeneracy of state M. If it's not equal to 0, then it's just an expression that contains the dissociation energy. Okay, so now what we want to know is the fractions of molecules in a particular electronic transition. So again, we're just ground upper excited state. We're really only thinking about 2 levels here. And if you look at it and go back to our definition of our fraction of the electronic state, we have the degeneracy at whatever state M we're in, and then we have the energy term here, and we have the partition function, okay? And then this reduces to this expression here for a simple harmonic model of the vibrational state. And such the fraction of the electronic is 1. And this should make sense. Again, this is before we do any excitation, and we've said at reasonable temperatures that pretty much everything lies in the lower electronic state, and this is what we get when we apply our simple harmonic model. Okay, so right now, everything's lying in the lower electronic state. Now, let's look at the vibrational partition function. Again, we have to put a term in for the vibrational energy. Remember, we did several or a few different versions. We had the simple harmonic oscillator, and then we had the enharmonic terms, correction. So that's what would go in this term, and then we sum overall, and we end up finding that the vibrational partition function for just the harmonic oscillator can be written as the exponential of, this is the reduced Planck's constant, so that's h over 2 pi. This is the frequency, vibrational frequency, divided by 2 kT. And then the denominator of the vibrational partition function is 1 minus this exact same term. So now, looking at the fractions in a particular vibrational level, we end up with the fraction of the molecules in a particular vibration level is given, there's the actual vibrational level, that may be V equals 0, 1, 2, etc. Then we have the vibrational frequency, which is characteristic for that molecule. Okay? And this right here will give you the fraction. Okay? Depending, obviously, you can probably see here that when this term is large, so low t, this value will be very large. So the fraction will tend toward 1 for low temperatures. So now the rotational partition function is just given by summation of all the rotational energies. And then we have to look at the particular, we can look at or model our rigid rotator. We did this, in the basic spectroscopy section. Or we can add centrifugal distortion. So every time we add another term, it's more complicated. So if we look at just our rigid rotor model right now, the rotational partition function is written in this manner. This is just a substitution of the rotational energy in here. The spectroscopic constant, remember we can write it in terms of, we had spectroscopic unit and SI units, and we manipulated this a few different times. So this is just the expression where it's Planck's constant, it's about 8 pi squared speed of light and the moment of inertia. Now, this term, kBT over hCB, is also T, if you look at the units for hCB over K, it's actually a temperature. It has units Kelvin. So this is what's referred to as the rotational temperature, okay? And since T, the actual gas temperature of the rotational temperature, typically is large, then we can replace the summation with integration. We can just integrate the term, and we end up with that the rotational partition function is actually equal to this term here. Okay? So now we can look at the fraction by looking at the energy that's in any jth rotational line divided by the partition function, and we get out this expression here. So remember, what we've done for the vibrational, for the rotational, is that now what we're looking at is this tells you the fraction that's lying just in the particular individual rotational or vibrational state. So if you put them all together, if we tune our laser to any particular transition, remember that will be most likely one or a few rotational transitions that, again, when I say a few, it's because we may overlap them by accident or just due to the bandwidth of the laser or due to their proximity. But let's keep in mind, let's say we're tuning to an isolated rotational vibrational transition. We end up interacting with one, again, quantum state, and this is the fraction that lies. Of all the population, this is the amount that lies. We have our information of the particular J transition that we're accessing, okay? And we have the particular V vibrational state that we're accessing. For every molecule, the values of B are known in the characteristic vibrational frequency, or these are particular to a given molecule, okay? So this would tell you if you wanted to figure out how many, in terms of how many of your total number density, what fraction of the total number density were you actually exciting and sending to the excited state. So let's consider example OH molecule. Let's say we excite the R18 line of the 1,0 vibrational band. Okay, so that means, again, we're going to excite in the ground state and send it to V equals 1 in the upper excited state. Okay, going from the X to the A system, and we're accessing quantum number 8. Sorry, rotational quantum number. J equals 8, I think, or N equals 8. So if we go into that calculation and plug in these numbers, let's just take a couple representative temperatures at 600 K, 99.99% lie in the V prime equals 0 band. What you would do is you just plug in whatever vibrational system you want to look at. You set V is equal to 0, and you see what the fraction comes out. You set V equals 1, see what fraction comes out. Pretty much everything's lying in the lower vibrational band. But at 2,000 Kelvin, only 93% is. So that means you have 7% distributed amongst V prime equals 1, 2, etc., with the majority of it being obviously in V prime equals 1. Again, let's look at, since you excited this particular N is equal 8, which is also because this is spin, this is J equals 8.5. At 600 K, 2.1% are in this transition. But if we were at 2,000 K, 8% of the molecules are in this rotational band. So for this particular transition, you get an increase in population with an increase in temperature. So this is kind of how the population looks for OH, and this is what gives rise to the structure of a spectra. If we look at 300 K, you can see only a few rotational levels are populated. It dies off by N is equal to 8. You've already died off with your lower J or your N states, J plus the spin, J plus S. Only 1 and 2 are your most heavily populated, and they die off very quickly to N equals 8. And your spectra looks like that. These are all the different, say, 2 through 8s, but you have your P, Q, R, S. All these different branches, all of them have a different same set of quantum numbers, so that's why it looks like a fairly congested spectra. Now at 2,000, you can see that, again, down these lower, this is 8, 7, 6, 5, 4. By the time you get down to 2, it's very lower, not very highly populated. Remember we said as temperatures, for certain rotational lines, they'll actually depopulate and you'll populate others. Your peak now is N is equal to 8, which for 300 K essentially had no population. It's this little line here. But now your peak population is N is equal to 8, and you can see population well down through N is equal to 24 and beyond. Okay? And now that's why you get this kind of characteristic spectra that's much broader. And what you've seen if you've looked at spectra before, whether simulated or measured, is that you see a shift in with increasing temperature of where your peak lines are. That's just due to the fact that your population is changing the different rotational lines and in some in vibrational states. So if you noticed on those simulations I've shown on where I've started off, and I've shown sort of the 0, 0, 1, 0, 2, 0, I've always given a simulation for about 2,000 K, right? And that's just, and you'll see this little bit of population in the higher vibrational states. If you do that for 300, you'll see nothing really beyond V is equal to 0. Okay, so that tells you how it's populated. Let's look at collisional dynamics. So if you want a quantitative interpretation of the LIF signal, you need knowledge of both the spectroscopy and the collisional dynamics. So we've talked about the fact that we have line broadening and shifting due to the collisions. But again, these collisions, probably the thing that we're most concerned about is that they cause non-radiative energy transfer. Again, that's the de-excitation of the upper state, okay? We have energy, it's called non-radiative because we don't get light out of it, right? We have energy transfer due to something running into it, and we don't get to see those photons. We lose that energy, we don't get that information, okay? So we depopulate the excited state, and we have a loss of fluorescence signal. We have the different non-radiative transfer mechanism that we've already talked about, or rotational and vibrational energy transfer, and then electronic energy transfer. Again, you can, all of these are, once you appreciate kind of the bird's eye view, they make a lot of sense. Collisions are redistributing things amongst the rotational and the vibrational levels, and collisional quenching, if you will, where we remove all signal, is because you have transferred the energy via collision from the upper electronic state back down to the ground state. And therefore, we have no opportunity to see that in terms of a radiative loss. So we've moved it from one electronic state to the other, and we've lost all opportunity to see those photons. Okay. Now, the energy transfer or quenching is the simplest of the collision-induced depopulation. This is one we'll talk about. It's much simpler than RET or VET. Again, we know that this process, we've described this quite a bit. This is where a fraction of the laser-excited absorber is de-excited due to collisions. And now the rate, this Q21, remember keeping still within our model of just two states where we have the ground state coupled to an excited state just via laser coupling, is going to be proportional, obviously, to a cross-section. Okay, this is collisions. And we have an N, which is a number density. Okay? And the cross-section, which we're called the electronic quenching cross-section, is a function of all the colliding species, and it changes as a function of those species. And it's a function of temperature. Okay? So the cross-section, again, a partner between, if you're, let's say, doing a measurement in OH, the collision cross-section between OH and water, OH and nitrogen are different. OH and water is different than that of OH and nitrogen and OH and oxygen. So every collision partner has a different collision species, and it changes as a function of temperature. Then the collision rate is also multiplied times the mean molecular speed of whatever species you're actually looking, not the collision partners, but VI. So again, if you're doing a measurement of NO, this is the mean molecular speed of NO, 8 kT over pi mi. But we can already see that we have a temperature dependence here in the cross-section, and we have a temperature dependence in the mean molecular speed. So the quenching rate is quite temperature dependent, or can be quite temperature dependent. Now, we sum all of these up, and we get the total electronic quenching cross-section. Okay, so we sum up all of our different species that we run into, and we can get an effective quenching cross-section. Okay? So again, they're molecular mass and temperature dependent of all the colliding species J. Okay? So this is in general how you deal with this. If we want our total cross-section that goes into our quenching rate, so we want to put in one value, we have to take all our different partners. So I is our species that we're doing the laser and fluorescence imaging on. J is all the other possible species that sit in the bath gas. And so you do this for all possible species at a given temperature, and that gives you the cross-section at T. Okay? And this all varies as a function of temperature. These are usually tabulated for a lot of species. And what means by tabulated is they're parameterized as a function of temperature themselves, okay? Such that they're a little bit more amenable to deal with. Now, RAT and VT, we've talked about a little bit, become important as the laser energy or their radiance gets really high. Okay, so if we have a higher radiance limit, these become significant. The relative importance, they're species specific, again the same as quenching, RET and VT depends on again, it depends on which species you're looking at, whether you're OH or NO, whatever system you're looking at for the fluorescence process, RET and VT are different. RET does not seem to be a function of this particular vibrational state that you're looking at. So once you know one set of RET rates, they're good for any vibrational state. Okay. They're calculated in sort of an analogous manner. You do some, again, in some ways you do some measurements, you figure out the transfer, and then they're effectively put into kind of a parameterization with cross sections. So again, you go in and you look up the rates. They tend to have a lot more uncertainty than collisional quenching rates. Now in general, if we're working within the lower radiance limit, because most of the time we'll work within the linear regime for fluorescence, and for kind of typical flame conditions, RET and VT may be omitted. And again, it really depends on what species you're looking at it. So there's no general statement that you can say. And most people will ignore RET and VT for a majority of the experiments. Okay, let's come back to the fluorescence signal and kind of put a lot of this together. We ended with this total number of photons collected, and we were still left with a lot of these terms that don't seem that we could just plug a number in very quickly. Okay? So, but since then we've looked at terms that are going to help us get rid of this absorption rate times this initial population in whatever quantum state we investigate. Okay? We also are going to lump all of these experimental parameters. So if we have a collection volume and we have efficiency, we'll call that just a single constant called COP. You have to calibrate that out anyway in any experiment. So once we do that, our fluorescence equation is now written at something that probably looks more like what you've seen in literature. Okay? We have just our optics system. We have the Ni, okay, which is the initial population. We have our we have our spectral irradiance here. And then we sum up all possible excitation transitions where we have the Boltzmann fraction. Okay? So this is now the number density of species I. This is no longer particular to any state. This is the total number density at I. So this is really what we want to find, right? Laser-induced fluorescence, we actually want signals proportional to number density. And this is how it's proportional. We end up, it's through this term here. This is all possible excitation. This gives us the population for whatever we excite. This gives us the overlap between our laser and the absorption transition. This is the Einstein coefficient. This is our efficiency, our Stern-Volmer, and this is the duration over which it occurred. Now, the reason we have this is, again, like for that NO example I showed where the line may overlap several line transitions, you have to do this for every transition, right? Because if the tail of my laser is touching part of an absorption transition, I'm going to get some photons from that, so I have to account that. So you have to look at all possible transitions. Okay? Now, the way you still to get kind of quantitative measurements, let's say your target is number density, or then knowing P and K, obviously you want to get temperature, or you want to get constant, say you know P and T, you want to actually get mole fraction, or you want concentration, whatever what you want from the measurement, you need to, one, get rid of this term right here, okay? And so quantitative measurements are typically made by referencing signals to other signals at known equations. You can imagine now if you take and divide this signal by something at a known condition, the COPs will cancel, right? You'd have a ratio of your signal and your process that you're interested in over your reference signal. And then you would have a reference number density that, say, you knew, and then you would have to know all of these other factors, and they all cancel, or you know them, okay? Other calibrations are certain things such as Rayleigh scattering or absorption. An absorption measurement where, say, you know the quantity and the path length, or you use an absorption measurement to get the number density from a reference case, and then you normalize. Rayleigh scattering with proper calibration can give you the number density as well. All I'm pointing out is that if you see these kind of calibrations in the literature, all they are used such that you can take and get an actual number density from your measured signal. The things you have to end up normalizing out your actually experimental to see opt, okay? But then when you're normalizing by a reference condition, you have to know all these things about your reference condition. Okay? So as you can see for laser-induced fluorescence measurement, there's a lot of parameters you have to control or you have to know for a quantitative measurement. Let's look at some examples, okay? Some more just visualization, how it's typically used, not necessarily quantitative measurements, but OH PLIF. It's perhaps the most utilized molecule in combustion. There's a lot of OH around. There's thousands of ppm usually. The excitation strategy is fairly straightforward. It's in the UV, but it's just the frequency doubling of dye laser output. You can spectrally separate the emission from the excitation line. These are normal strategies, 282 for the 1-0 transition or 306 for the 0-0. Okay, it's a great marker of the combustion products. In turbulent transport, it's not quickly destroyed. It's destroyed very slowly by three-body reaction. Okay? And again, you get very high signals. Okay? So no one really ever struggles to see OH. Okay? So you're in flame conditions. Okay? Now, it's primarily used for visualization, such in this case, to see where the products are, where the flame is. But it is actually one of the easier species to put on a quantitative basis. Now, if we want to do a quantitative measurement, looking back at our fluorescent signal equation, the most challenging aspects is the fact that you have all of these temperature-dependent parameters, right? You have a temperature dependence in your Boltzmann fraction. You have a temperature dependence in your overlap integral. You have a temperature dependence in your quenching rate. So what you want to do is you want to make a judicious selection of the rotational line. In that way, you end up finding that you can remove the temperature dependence such that the fluorescent signal is proportional to the mole fraction or concentration. So lots of time, even in visualization, because you want to be able to say, okay, when I get the signal, it's somewhat proportional to my number density. You want something that's temperature insensitive, right? And so the n equals 8 rotational line, or the J is equal to 8.5, anywhere from like 7.5 to 9.5 are used. They have very little temperature sensitivity for T is greater than 1300. The reason why that's important is that you really don't see OH until about 1000, 1100 Kelvin. I did a Boltzmann fraction down to 500, but it's not like you're going to see OH there. Okay, this is just a calculation. So these are the temperature ranges to where you typically will actually see appreciable OH and detect it. And over that range, the Boltzmann fraction is pretty flat. Okay, and then you can also see that it turns out that the quenching is pretty flat for these temperatures as well. So this is actually the excitation. This line gives a pretty reasonably where if you have a change in signal, it's likely due to the fact that you have an actual change in OH. CH is another marker that's used. CH is primarily used to visualize the reaction zone. Okay? So CH is excited, depends on your transition, 390 for the beta X, somewhere around 413 for the AX transition, or 314 for the CX transition. The reason why CH is used is it occurs during the final stages of fuel decomposition. It's unstable and short-lived, so you get these narrow, thin spatial distributions that mark regions of high reactivity. So in premixed flames, CH is commonly used to identify the flame front, and in non-premixed flames, it's the stoichiometric surface, which is referred to the flame in non-premixed combustion. It's the primary reaction zone. So again, here's some visualization in a highly turbulent premixed flame to look at the flame front via imaging in the CX system. And this is some of the more well-known first imaging with the BX system by Jeff Dunbar, Cam Carter, and co-workers, again, where they did velocity and reaction front imaging in a non-premixed flame. And you can see it has this very thin region, so you can actually look at all the curvature and all the wrinkling of the flame surface. Okay, and under turbulent condition, it's purely visualization. I haven't really seen anyone who's attempted to quantify the measurements. Okay. We all know the importance of NO. NOx are pollutants, heavily regulated. The formation destruction pathways under turbulent flame and engine conditions are not completely understood, and the measurements are valuable. So that's why we put so much effort in measuring it. NO is excited in the UV. The most common is 226 for the AX transition, but there's certainly the BX and CX transitions are used, and the DX, transitions are used, which are just other locations within the ultraviolet region. Quantitative imaging is tough. I did a lot of this in my graduate work. It's a challenge mainly due to quantification under where it's naturally occurring NO. You have two problems. You have very low signal levels because we know that NO occurs in like ppm levels, very low levels. It has significant quenching. The quenching rates for a lot of the species like oxygen and others are very high. And this leads to difficulty in quantification. In fact, the signal at times, the signal distribution doesn't look at all like the actual mole fraction type or concentration distribution. But here are some examples. Been done both in an engine type situation and in, again, a highly turbulent premixed flame. You can see the NO existing in the high temperature regions. Again, usually you end up when it's naturally occurring NO, very low to modest signal to noise ratio, and again, you have to be careful with the transitions you pick for quantification. Now, beyond these examples, there's certainly other species. CO, formaldehyde, HCNC, and others, but there's not an infinite list of species that can be excited via LIF and PLIF. So this kind of just gives some of the main ones. OHCH and NO are kind of your main ones, with a lot more people doing, in terms of visualization, formaldehyde and stuff these days for lower temperature areas. Okay. Finally, we can look at some of the strategies that have been used for reaction rate imaging. Obviously, it's a highly desired quantity to look at the reaction rates within the flames, but it's quite challenging. You'd want to measure a heat release rate, but there's no real way to measure this, so there's a few proxies. The first suggested approach involved imaging of HCO, as if you looked in laminar flames, the profile of HCO overlapped the profile of the heat release rate very well. But this molecule is amenable to excitation, but it's just very weak, okay? And so instead of doing that, what's been used a lot in the literature is the overlap between the formaldehyde distribution and the OH distribution, since it's formaldehyde plus OH goes to HCO plus water. So what you would do is you do multiple measurements, okay? You'd make an OH PLIF measurement, you make a formaldehyde PLIF measurement, and then their spatial overlap gives you kind of a proxy for the regions of heat release. And this is a visualization approach, but it does give you a pretty reasonable marker of reaction rate. Other approaches such as CO plus OH are used to look at this rate, which is a very important rate limiting reaction, hydrocarbon combustion, the CO plus OH reaction. So again, you would have an OH measurement, a 2-photon CO lift measurement, and their overlap gives you the forward reaction rate. Okay? All right, so for that finishes this lecture, again, which we're kind of bracketing them now over breaks. But at this point, I'll take questions on this particular lecture on the kind of the quantification of lift. We did absorption profiles, et cetera. We basically looked at along the y-axis, population, et cetera. So if anyone has any questions, we'll take them now. You're first. Okay.
So where exactly does that, where is the logic behind that show up?
So the fluorescence equation that's here is completely written on the fact that you have uniform illumination. But remember, everything's proportional to their radiance. So if you have a structure to your laser sheet, every local pixel, every local transfer is going to get a different irradiance, so you have to correct for that on a relative basis. So all measurements like done in my lab, we do laser sheet intensity corrections or beam corrections. They don't have a place in the theory, but we can certainly put them out in front and write that I as a function of x and y if you want to. But all that is saying that if you imagine, what he's asking is that all those are assumed that you have a uniform distribution of light hitting. But if you have some profile, right, distribution of your laser, right, I can draw this in case, let's say we have a laser sheet and we're doing an imaging here, right? That's assumed that if you were to take a profile of x, that you have some signal that looks like that, right? Some I, where this is. But what happens in reality, sometimes you have a laser sheet that looks like that, right? You have some structure in the beam, and you expand it out into a laser sheet. Well, what happens is this point right here will get less when this is transferred onto your camera. The pixel that has this point will get more signal than this point right here, just because the fluorescent signal is proportional to the local irradiance. So you have to do a separate measurement on the side, if you will, in a uniform sample of the marker, instantaneously measure your distribution, and then divide your image by that. If you divide by that, that puts everything on the proper basis.
Divide by a normalized line profile?
Well, you have to divide, right? You have to, because right here, the signal you're getting is low. It's been artificially pushed down low, so I need to divide by a small number to bring it back up. So you absolutely are reducing your dynamic range. You have to. But this is the only way you can put it on a proper basis, on a shot-to-shot basis. You have to divide by the actual instantaneous profile. Okay?
About the CH imaging
Yeah.
about, it occurs in the method for hydrogen flames?
Yes,
And
it doesn't exist.
Yeah, so is there any sort of replacement for, like, what's the best method for kind of?
So if you want to react like a flame front, like in a premix flame, you would take your OH and take the gradient of the image. Okay. Would be the best way to do it, because then at the front you'll have the highest gradient. But obviously if you can measure certain other things that are not as amenable to measurements, but kind of our basic stock, that would be the easiest one. Or seed in a small fraction of hydrocarbon, and then it's there. But for pure hydrogen, your best bet would take a OH spliff and then take the gradient. Because not only do you have the gradient due to the flame front, but typically near the flame front, you have super equilibrium amounts, and so you have an excess amount, so then when you take the gradient, it really gets magnified there. Okay? Other questions? That's it for PLIF then. Okay, let's move on to next topic. Okay, so now what we're going to do is moving from laser-induced fluorescence, we're going to move into spontaneous scattering measurements, okay? And we'll talk just general scattering quickly, and then we'll move kind of through three parts to finish out the lectures kind of on the particular topics. We'll look at Rayleigh scattering. We'll look at a modification to Rayleigh scattering, which is something called filtered Rayleigh scattering. And then we'll look at Raman scattering. And in Raman scattering, you can have both rotational and vibrational Raman scattering. Okay? So here's the goal of this lecture. We're going to provide an overview of Rayleigh and Raman scattering, and again with a particular focus for this lecture on Rayleigh scattering. We'll give the background of these scattering processes. We'll develop the Rayleigh scattering equations. They're developed in a different way than the fluorescence equations. We'll look at experimental considerations for when you're doing Rayleigh scattering, and then we'll look at applications of Rayleigh scattering in sort of turbulent reacting flows and even engine-type conditions. Okay, so let's talk a bit about scattering processes. It's not a resonant process. So unlike LIF, spontaneous scattering processes can be performed with any laser wavelength, and we'll show why in this lecture. But we have to understand that when we send in a laser or EM field, there's many different scattering processes we need to consider. Okay, we have Rayleigh scattering, which will be the focus of this, which is elastic scattering of a photon due to density fluctuations. And of the density fluctuations, it's just the random thermal fluctuations. Okay. We have Raman scattering, which is inelastic scattering due to a photon, scattering of a photon due to vibrational and rotational transitions in the bonds between neighboring atoms. So what happens, we're going to look at when we couple. We'll talk about a modulation of a dipole due to electric field. When it couples to either a rotational or vibrational transition, we can get Raman scattering. There's Brillouin scattering. This is an inelastic scattering of a photon due, again, these are density fluctuations, but these are now correlated periodic acoustic fluctuations, which in pure physics fields are referred to as phonons. We have Thomson scattering, which is elastic scattering of a photon by free charge particles, so electron scattering. And then we have Compton scattering, which is inelastic scattering of a photon by a free charge particle. We are typically, let's say we have only neutral gases, we'll consider these three, okay? And really, in kind of colloquial, you consider Rayleigh and Raman separately, but we'll turn out that this process, filtered Rayleigh scattering, we need to consider Brillouin scattering effects. And I'll define clearly what I mean by how you separate out Rayleigh and Brillouin scattering. Just through terminology over the years, there's not clear, kind of terminology has been kind of combined to what we really mean when we say Rayleigh scattering. We're actually referring to something that's Rayleigh and Brillouin scattering, okay, in gases. So that's why I have an asterisk besides Rayleigh. In the next lecture, we'll talk about filter Rayleigh, which I'll show that we're actually dealing with more. We're actually dealing with 4 scattering phenomena when we say Rayleigh scattering, or 3 scattering phenomena when we say Rayleigh scattering. Okay. All right, let's go back to our dipole. In lecture 9, we introduced the electric dipole, which is primarily as a means to, if you know, there was a slide, we moved into the dipole operator, and the transition dipole moment to examine absorption. Okay? So basically just introduce this as a very quick tool, so how we absorb a photon. For Rayleigh and Raman scattering, we'll actually use this formulism to develop the theory. I want to make sure it's clear, you can develop Rayleigh and Raman scattering equations through a quantum mechanics viewpoint. It's just using these dipole mechanisms and model are very straightforward, and so I like doing them with this classical method. So really what we're going to talk about is we're going to consider the electrons in atom or molecules, or even more generally, let's just say a small particle. Basically, when we force them to oscillate by applied electric field, i.e. what's this? This is our laser. An oscillating electric field, they're going to radiate like little dipole antennas. They're going to radiate at the frequency of our laser. So that's how we're going to describe this. Okay? The treatment of the scattering process as a simple emitting dipole is very accurate for monatomic gases, helium, argon, because they're spherical, no internal degrees of freedom. Okay? So it's actually a very good description. For molecules, this approximation weakens quite a bit due to changes, because when you have a molecule and you excite with electric field, the changes in the vibrational and rotational states occur during scattering. However, we'll show that we can correct for these, okay, and so that we can still use this same simple treatment. Okay. In lecture 9, we referred to a static dipole, but what we want to consider is the case of the interaction of electric field with a small particle. So what we're going to do, since the electric field is oscillating in time, we're going to consider electric dipole that's oscillating in time. All right, so now let's start building our formulism. Let's say that there's no spatial variation in the electric field. Let's just, for right now, consider just a single point, okay? The time-dependent expression for the incident electric field, if we model it as a harmonic oscillator, can easily be written as this. Our time-dependent solution of the electric field has some amplitude that's just modulated at some frequency omega. Right now, this is not the vibrational omega. This is just some generic frequency omega, okay? This actually turns out to be the laser frequency. But right now, so this is just an oscillating electric field. That's all this is, okay? Now, when the electric field interacts with the molecules, our protons and our electrons have to move in accordance with Coulomb's law, okay? I called this previously perturbing the electron cloud. Ooh, too many quotes. Perturbing the electron cloud. Really what you're doing, if you think about this, is we have this oscillating electric field that's coming in. What is the electric field? It's essentially a field that develops around a charge. We have the charge distribution within a molecule, okay? And depending on whatever distribution you have, we're going to move some electrons someplace, some protons are going to go different way, basically following Coulomb's law. Some are going to get close, some are going to get far away, right? And this is going to be happening over a time-dependent nature, over the oscillation period of the laser. So really all you can think about this is that you're putting there's a time-dependent charge on the molecule that's coming from the laser. All it is saying is we have some Q naught that exists there normally, and then we're modulating by the amplitude of the laser frequency, okay? You can just imagine that periodically as the laser comes through, whatever periodic, it's moving the electrons and protons around just due to their response due to the EM field, okay? So then it should be fairly straightforward to think that we have an instant electric field from our laser produces an oscillating dipole moment, okay? Remember, we have a dipole moment that's just the just the charge times the distance between the two nuclei, so D. But then if we're modulating the charge, here Q, right? That means we're modulating the dipole moment. So hopefully we're already there. We're modulating the dipole moment. Okay. So once an oscillating dipole is generated, an oscillating electric field propagates away from the dipole. So let's think about this at one point in time. We have electric field that comes in. At one point in time, we generate a dipole moment. And what happens is that has to propagate away. And since we continue to oscillate that, we end up with this character. This is a static dipole. This looks like the electric field around a dipole. But since we're now modulating it, this is actually what your field will look like, right? So you can see it's propagating away, and you can see the characteristic frequency of the modulation of the laser on it. So the oscillating electron field as a function of R, which is away from the source, right, looks like this. We have our dipole moment. We have whatever the frequency, driving frequency is, omega squared. We have a projection here, okay? Now let's see, do I have that on this slide? No, okay. We have our projection of psi. Let's see, if we're an observer and we're at an angle phi, we are going to see a projection onto a certain plane. So we're going to see an apparent dipole. So all that is geometry. We have our time-dependent solution, and we have our distance r that we're moving away, and we need this normalized by the speed of light, okay? So this just turns out to be our oscillating dipole. This is our propagating electric field away as a function r, distance, and sort of an observation angle, okay? So this is just a generic observation angle with respect to the polarization of the incident electric field. So we now have a time-dependent solution for the electric field. Now, let's look at the simple case. Let's talk about an atom, if we will, or let's just say we have a spherically symmetric molecule. If it's spherically symmetric, P is induced, P vector is induced in the same direction as the incident field polarization. So if I have a polarization in a certain direction, the dipole moment is in the same way, and it's linear proportional to the electric field. Okay? So its proportionality constant is a scalar if it's in the same direction, and this is the polarizability, which describes the relative tendency of a charge distribution, the electron cloud to be displaced. Remember, we talked about polarizability. This is how susceptible a molecule is to being polarized by the actual incident electric field of the laser. Okay? So this is kind of, think about again as an efficiency. But since our dipole moment has to be in the exact same direction as the incident field polarization, it's a scalar. Now we also had this polarization vector where we described in lecture 2 as the susceptibility, as the ability of dipoles to respond to a polarizing electric field. It sounds a lot like the same thing. So let's talk about this a little bit and why we have two definitions for the same thing. The average susceptibility is related to the polarizability through the Clausius-Mosetti relation. So this is the susceptibility, this is the polarizability, this is again the permittivity or the dielectric constant, and this is the number density contributing to the polarization. Okay, so why do we have two parameters that seem to describe sort of this tendency or this kind of ability of a material to be polarized by the electric field? So it's because we kind of have an overall applied field and we have a local electric field. So what I wrote here is that you have the local electric field can differ significantly from the overall applied field. Okay? So the way that I think about it is that the measurement of the susceptibility describes the electric field, okay? And the measurement of the polarizability describes the applied field minus the effect produced by the dipole. So locally, you're going to have the effect of the entire field, but you have some effect by the induced dipole as well. So it's kind of a local effect and a global effect. Okay, now let's get back to things that are going to start looking like molecules moving a bit, or at least moving, oscillating. We have an oscillating electric field. That means the dipole moment must also oscillate, right? But we had a definition for the dipole moment in terms of alpha E. So now we have an oscillating field that looks like this. So our dipole moment is now written as alpha, okay, times our electric field vector, amplitude of the electric field vector, cosine omega t. So now we want to see what happens if we end up coupling to something. So right now, this right here, this previous equation right here, shows you the amplitude of the again, the dipole moment. Essentially, this is the emission. We'll get to this, but this is essentially already the scattering. This is the emitted dipole oscillating due to the oscillating electric field. So all you're getting is whatever frequency the electric field the laser's oscillating at, you get basically back light coming back at the exact same frequency. Now we want to see how that's divided up. Let's say in addition to translation of the molecule, we actually have internal motion. Okay? That would be electronic, vibrational, or rotational energy. Okay? So now what we just described for something that's spherical, if we're just sitting there and we hit an electric field, it's going to respond, modulate at the exact same frequency as the laser, right? We're saying we're emitting a dipole. But now, if we have a molecule, now we have vibrational movement and rotational movement. So we have rotational movement, vibrational movement. At the same time, we're modulating it with the electric field, okay? The modulation from the molecule, the movement from the molecule can actually modulate the induced oscillating dipole. Okay, so if we have no movement, we get an oscillating dipole, we get this emitting antenna, but now the actual motion of the molecule itself will now modulate that movement. So we can put another frequency on top of that frequency, okay? So the oscillating dipole is at the frequency of the laser, whatever gigahertz the laser is at, right? Now whatever vibrational frequency that the molecule moves at, we will add that on top of that induced dipole, and whatever rotational frequency is, we can add that on top as well, okay? So these cause a different frequencies, right? If you take two frequencies, you know, just even in signal processing, if I have a certain frequency and I throw another frequency on top of it, I have a different frequency, right? And so these are different frequencies that are going to appear. Okay? So in this way, we can write the polarizability as the combination of what's called a static term, okay, and an oscillating term that now has the modulation frequency in. So this, remember, the alpha was a scalar. It's now whatever its original static term is, and then we're going to write another term that has this additional modulation frequency. Whatever this frequency, whether it's coming from the vibrational or the rotational is, we'll deal with each one of them separately. So the modulation at omega m, which is coming from the actual molecule itself, causes the dipole moment to oscillate at different frequencies other than omega, which is the laser frequency, which is characteristic of the incident field. Okay, incident electric field, laser. So now we can write that the dipole moment is written in this manner. The dipole moment is our static term modulated at the electric field frequency. Sorry, it's our static term times the modulation at the electric field frequency, and then this term that is again modulating this frequency such that we have a different total modulation. So let me just say oscillating. We have our original term that's oscillating at the frequency of laser, and then we've now modulated that frequency such that we have a new frequency coming out on top in addition to the original frequency. So if you manipulate that, you end up with this expression that the dipole moment, we have this static term. Again, this is what we would expect. This is fluctuating or oscillating at the laser frequency. Now we have a different frequency that is lost, that is omega minus omega m, okay, and omega plus omega m, okay? What we have here is this turns out to be the Rayleigh scattering, okay? And then what we have here are Stokes and anti-Stokes scattering, okay? We gained energy, we lost energy. Okay? I haven't called them Raman yet because we need to do a little bit more to call them that. But we have our Rayleigh, this is what's coming out essentially at the same frequency, the same light. I will show that that's not exactly right either. But we have our Rayleigh, and then we have these ones that are being modulated. Now remember, this frequency can be either the vibrational frequency, which may be a couple thousand wave numbers or something like that, or these can be the rotational frequencies, which would be single wave numbers, okay? So again, keep in mind, this is just right now any generic motion from the molecule. Now, the oscillating portion of the polarizability can be related to the physical molecule, okay? So let's, by recognizing that the ability to perturb this electron cloud really depends on the relative position of the individual atoms, okay? So the polarizability turns out to be a function of the instantaneous position of the atoms. So again, a lot of here, just let's try to find out the key points. Energy levels are quantized, okay? So the displacement of individual atoms have to correspond to specific rotational and vibrational modes. It can't just be any random energy. So if we focus on vibration first, let's talk about vibration. Let's see the displacement of any atom about some equilibrium position due to its vibrational mode. Again, its displacement due to vibration is now also written as Qs. Qs, spectroscopy loves Qs. We have Qs. Q naught is the amplitude of the vibration about the equilibrium position. And omega vibe, if you will, is the vibrational frequency. All this is saying is that the ability to move an atom out of its place is a function of its actual vibrational mode. So now, you can see the displacement from its equilibrium position is small because the movement due to vibration is very small. So we can do a Taylor expansion, and now the polarizability can be written as alpha is just alpha naught, which is its equilibrium position, and then the relative change of the polarization to partial Q. We go partial Q, where again Q is the amplitude of the vibration, amplitude of the variation. So let's substitute all that back in, and we'll see where this goes. We can see that this is now back to P vector, your dipole, induced dipole moment. We now have Rayleigh, Stokes, and Raman again. We now just have this term in here has just been substituted in. So the reason why we write that is that what we can try to say now from this, hopefully all of this, even if the last couple steps, you need to work out on your own with pen and paper, when you get to this point, this is hopefully attaches you a little bit to the physical. What we can say is that when we induce a molecule, hit it with an electric field, if the polarizability does not change with vibration, okay, then there is no vibrational Raman effect, okay? And you would only be left with a static term. So if this term is 0, all of this goes to 0, okay? So really, in order to have Raman, in order to have vibrational Raman or even rotational Raman, we'll talk about, in order to have the vibrational Raman effect, there needs to be a change in the polarizability with vibration, right? And so the other way to state this is for vibrational Raman effect to occur, the vibrational change, a vibrational change results in a change in the polarizability. So all we're trying to say is that when we hit with electric field any molecule, there's a certain polarizability. That's a material property. We talked about that's a material property. And if it changes with vibration, then there has to be a Raman effect. If it doesn't, it's not the Raman effect. So we'll stop here after these two definitions so we can actually see a little bit. Rayleigh scattering. If the induced polarization does not couple with polarization oscillations due to vibration, then the vibrational state of the molecule is unperturbed. So this thing just keeps on vibrating like it was, okay? So what can happen, let's think about this. I can send an electric field, and I can actually modulate that vibration. It can be happy doing this, and I can add a little modulation to it. If I do that, then I'm going to get out vibrational Raman. If this thing is vibrating, and when I send an electric field and nothing couples to it, there's no Raman effect, okay? If that happens, then the scattered photon, this emitted dipole, is at the exact same energy or the optical frequency as the original photon. This is quote-unquote elastic scattering. Now, if the induced polarization, which is, again, all that means is the interaction of the electric field with the molecule, if the induced polarization couples to a vibrational state, then this corresponds to vibrational excitation. We have excited vibration. We've caused it to vibrate at a slightly different frequency. Then those scattered photons are at different energies as the original, and we've gained or lost energy, right? Because if I take some of my electric field and couple to it, then I've added energy to the system or I've removed energy from the system. It really depends on how it's coupled, and we'll talk about that tomorrow. But if we do that, then the frequency that's emitted has to be different, and that is Raman scattering, okay? So we'll stop right here for now, but I'll take some questions just on these first kind of few slides on this in case there's questions on kind of how we set up the problem. If not, we'll meet back at 4:30 or 4:33. Any questions? All right, take your break, and then we'll meet back in 15 minutes.